Today I'd like to talk to you about how adding the mesoscale in our models might improve large-scale climate variability and change and climate projections. And there will be a bit of a scattering of topics. I'm mostly going to focus on, as Malcolm said, how improvements in the ITZ could help for simulating SST trends in the tropical Pacific, the Pacific in general. But I wanted to show you also a little bit about this work that I think is very relevant to EERIE about how increased atmospheric resolution can help uh, re resolve the mid-latitude vertical coupling that's important for how the atmosphere responds to mid-latitude SST anomalies and simulating mesoscale frontal processes such as you can see in this picture here. So wanted to just start off with a thing that I think we're all on the same page about, but it's always good to say anyway. So what are we simulating when we're moving to higher resolution than the typical the 100-kilometer resolution of climate models? So I think I won't focus as much on the left here, because this is really what this project's all about, is simulating these ocean eddies. But I'm going to talk a little bit more about how increased atmospheric resolution is benefiting from pushing towards this 10-kilometer scale that ERIE is working on. And so focusing on, for example, these you can see that doesn't work. This nice front here is something that is not going to be well resolved in a 100-kilometer model, and then might be resolved better in 10-kilometer or even higher, if possible, resolution. And then, of course, there's interesting implications if you're then coupling that to the ocean as in ERIE, and how these mesoscale features in the atmosphere are then interacting with the mesoscale features in the ocean. I think that's a really exciting opportunity for ERIE to look into. I'll talk a little bit about also how topographic resolution is important, and just wanted to briefly see that here, showing differences in what the topography looks like between 90-kilometer and 30-kilometer resolution over Europe on top, and then focusing on more in the region I'm going to be focusing on in the talk about the SST trends in the East Pacific. There's important topography in Central America that's shown here, where you can see in the black line on the bottom right, what the actual maximum elevation of topography as you go down the Central American peninsula, how high it is, and then how 50-kilometer or 100-kilometer resolution then smooths that to basically get rid of these high elevation mountains there that are then important in blocking the flow and shaping the trade winds in the East Pacific, with important implications that were explored in a really nice paper by Jane Baldwin in 2021. So most of what I'm going to talk about today is then how increasing resolution to resolve these mesoscale processes, in particular in the atmosphere, might help with some climate model problems. So I'm primarily going to be talking about the pattern of Pacific SST and circulation trends since 1980, and why that's not well reproduced by CMIP models. But I'll talk a little bit also about the too weak atmospheric decadal variability in mid-latitudes and how that relates to coupling with SST anomalies in the mid-latitudes. And this will all be framed in terms of how high resolution might help with these issues. So showing that reduced mean state biases, such as in the double ITZ, might help you get this warming pattern correct. And then showing how this vertical coupling by resolving atmospheric fronts might help to get these responses to SST variability in the mid-latitudes that then gives you also decadal variability in the atmosphere. I'll end with a bit of a brief perspective on the future of high-resolution climate modeling and what we can take away from this. So let's start by talking about this SST trend pattern problem and how that double ITZ bias is involved with that. So first, a bit of an introduction on this problem. The tropical Pacific is not changing as expected. You see on the top the observed trends since 1979 here through 2020, and then comparison to the average over many climate model ensembles. So basically the average climate model response over this period in hindcasts looks much more spatially uniform, a bit of eastern intensified warming compared to the observed changes, which have this East Pacific cooling that extends also into the Southeast Pacific, into the Southern Ocean, and then Western Pacific warming, and also into the Indo-Pacific. So quite a different pattern of SST change. And this is not quite a fair comparison. You're comparing a single realization of the real world with an average over many climate models that have averaged out all of their internal variability. But if you look through all the different ensemble members of the many models that have run large ensembles, these are all the CMIP5 and CMIP6 large ensembles. Looking at, say, a particular index like shown here, the West minus East Pacific SST difference, there's very few that can get observed changes, which are all the way at the right side. Try this again, I think it's not working. This observed change in this East-West SST difference is quite at the edge of what models can simulate. So these CMIP class models. And this is just one index, but it's true also for many different regions you might look at. So for example, the Southern Ocean SST trends have been cooling in observations, and this is really at the edge of what models can simulate as well. So all these different CMIP5 and CMIP6 models, very few can simulate this cooling of the Southern Ocean. There's some GFDL models that have tons of multi-decadal variability there, and then they can simulate this, but most of the rest of the models cannot. But if you compare between these two indices, the tropical Pacific SST gradient and Southern Ocean, the models that are able to capture the observed trends are different models between these two indices. So even just with these two indices of how the SST pattern is changing, no single ensemble member out of the 600 ensemble members I'm looking at here can reproduce the trends in these two indices. So there's clearly some pattern, SST trend pattern problem going on, with the models not quite getting the right answer. Wanted to show one other interesting analysis from the same paper that tries to characterize how this discrepancy has been evolving in space and time using a variant of signal to noise maximizing EOFs. But basically what this does is it finds the anomalies that are most different between observations and the models and how they evolve in time in kind of an EOF type perspective. So then you can see an SST and sea level pressure is also included in this analysis, how these SST and sea level pressure anomalies look as a spatial pattern and how this discrepancy has evolved in time in the observations shown in black and orange lines compared to all the models. So then there's this pattern of, let's call it IPO-like SST changes with its teleconnections also into the higher latitudes showing up in sea level pressure that no ensemble member from these 16 different models, 600 members, is even getting close to correct. It seems to evolve particularly from 1979 to about 2003, and then it's kind of flatlined since then. So the discrepancies trend is coming a bit earlier. It's not quite ongoing still, but it hasn't reverted back. So we're still not sure if this is decadal variability, if there's some non-greenhouse gas forcing, such as aerosols or ozone, that was important in this early period. But it maybe gives a sense. You can kind of come up with different hypotheses for what could explain this kind of timing. Most likely, multi-decadal variability is involved in some way, but there's certainly, it's unlikely to be the whole story, and I think there's a good case to be made that forcing is involved as well. So now I want to jump to what high resolution can help with this problem, because I was just showing how none of the CMIP models are reproducing this pattern. But then there is this exciting result coming out of the CSM modeling community that the high resolution version of CSM, which has a 1 degree atmospheric resolution, quarter degree atmospheric resolution and a 10th of a degree ocean resolution, can actually reproduce this SST trend. And importantly, they've ran more than a single ensemble member of these historical simulations. They've run 4 here with more coming soon. And even in this 4-member mean, you're looking much more like observation. So this is saying that this model is capturing this SST change as a forced response. And this is very comparable to the low resolution version of the same model with 1 degree resolution in the atmosphere and ocean. And this then, shown on the right, does not capture this SST change. So it's showing just by changing the resolution in the atmosphere and ocean, you're better able to capture this observed SST pattern. And this is quite robust to sampling. The open circles that are all over the place on the middle map are showing where the high resolution ensemble is outside the distribution of any possible sampling of the low resolution ensemble. But this isn't the case for all high-res models. I'm highlighting a paper that's, well, this is from an EGU abstract, but there's a paper coming soon. I've talked to the lead author, and it's still under review. But there's no consistent improvement as you increase resolution. So if you look at high-res MIP models, they don't necessarily do that much better than CMIP on average in simulating this SST trend pattern. So what's going on in CSM? Why is it able to simulate this pattern? So I'll show it in a little bit different way here, showing this is the SST trends just over half of the year in austral, winter, and spring. And superimposed on top of this, also showing some wind trends, but then importantly, I want to draw your attention to the black contours, which are the climatological rainfall. And unlike what you'd see in many other models, there's no second ITZ band in the Southeast Pacific. And what this allows is when you have some initial relative warming minimum showing up in the Southeast Pacific, as occurs due to the higher evaporation there, this then can propagate into the tropical Pacific through the wind evaporative SST feedback, which was nicely introduced yesterday, where it can trigger basically the whole ENSO system and then trigger rainfall anomalies at the edge of the convection in the West Pacific that then trigger these teleconnections back into the Southern Ocean that then can reinforce this initial cooling by modifying the winds and currents off the coast of South America. And this two-way teleconnection between the Southern Ocean and the tropical Pacific was discussed in a paper by Dong et al. 2022 in the context of some atmosphere-only simulations, but then this is basically showing how it plays out in the context of climate change in these coupled high-resolution simulations. So what's the ITZ have to do with this? I showed it's not there in this model, but then this is showing what the low-resolution CSM looks like. And you can see this extra band of rainfall. Sorry, I can't point it out, but it kind of extends off the equator from South America into the South Pacific. And then when this initial relative warming minimum shows up due to the high evaporation there, it starts to propagate towards the tropics, but then it reaches this double ITZ, which now is labeled there. And basically this convection allows the SST anomaly to be damped away. This convection moves it up into the upper atmosphere so that it no longer continues to propagate into the equator, and it doesn't trigger quite as much ENSO connections, which then don't trigger this reinforcing feedback. So then when you have this initial pattern warming, it isn't reinforced by this two-way teleconnection feedback loop. Interestingly, CSM has also run a mixed resolution ensemble, and I think this is really important for understanding why it has these improvements. So this is showing CSM run with a 25-kilometer atmosphere and 100-kilometer ocean. So then the ocean is kept at the low resolution, only the atmospheric resolution is increased. ITZZ is still gone. You have a little bit of this SST trend pattern. If I go back 2 slides to the high resolution, it's not quite as dramatic of cooling and West Pacific warming, but it's getting close. So I think it solves the ITZ part of this problem, but then is missing some additional boost of Southern Ocean cooling. So it seems to indicate that ocean resolution might help with this, the Southern Ocean cooling part of it, but that a big part of what's going wrong with the tropical Pacific patterns is coming from the ITZ bias and the atmospheric resolution. So this was all in one model, but I want to show you some evidence that this also holds across other models using the CMIP archive. Because while this double ITZ bias has been around in CMIP models for a long time, there are some in CMIP 6 that are doing quite good. So this is showing a histogram of a double ITZ index, which basically focuses on this box in the Southeast Pacific, where if you show on the left-hand side, the observations compared to the typical climate model, there's a huge difference in rainfall. There's no rainfall band there in observations, and there's this extra erroneous rainfall band in the typical climate model. So if you just look at the maximum value of climatological precipitation in the season DJFM AM, this is most of a problem. This creates an index of the double ITZ. And I'm showing on the right-hand side a histogram of all the CMIP models and also CSM 1, HR, and LR, and observations. So there's this dramatic improvement between the low resolution and high resolution CSM, but there's actually 5 CMIP 6 models that do better than this, and one that's really right on with observations. So do they then show the same mechanism that these low ITZ bias models can better simulate recent trends in the Pacific? And I'm going to show that they do. So here first is one aspect of this result, which is that the long-term trends, so this is looking at 1975 to 2014 to stick in the historical simulations, show the low ITZ bias model shown in the middle show a pattern that is robustly more like the observations than the high ITZ bias models. It's not quite showing as dramatic of an improvement as the high resolution CSM, but there is this relative warming minimum in the Southeast Pacific that then propagates all the way to the equator. It propagates a little bit too far west compared to what's happening in observations. And so you end up with a relative warming minimum in the Central Pacific instead of the East Pacific. I think this has to do with the cold tongue extending too far west in these models still. But in models that have a large ITZ bias, you don't get this propagation of the relative warming minimum to the equator at all. And so there is a significant difference between these two. And while this doesn't quite explain all the way to the observations, another interesting result that came out of this work is that these models also have much stronger multi-decadal variability in SSTs in the tropical Pacific. And so here it's significant everywhere. These models have much more decadal variability throughout the tropical, subtropical, and subtropical Pacific and Indo-Pacific. And this is somewhat in line with observations. It's a hard quantity to calculate in observations because you have to know what's the forced response and remove that. Tried a few different methods of doing that, and it's mostly robust to that. The observations look more like the low ITZ bias models than the high ITZ bias models in terms of this decadal variability. And it's been discussed for a long time that the CMIP models have too little decadal variability compared to some, for example, paleoclimate records as well. And so it seems like this could be fixed also by fixing this double ITZ problem that's been around in climate models for many decades. So we think we're closer to understanding why the historical SST trends are not showing the same thing in models and observations, that it has to do with the double ITZ bias, that this doesn't have to be just a resolution thing, that if you can fix the double ITZ bias also by other means than resolution, that this will also improve your simulation of historical SST changes. This is all about the historical period, but wanted to discuss briefly what we can expect for the future. So we still have, for example, paleoclimate records that show that there's eastern intensified warming in the warm climates of the ancient past. There's also physical understanding of why this should occur. So we still think that the East Pacific will eventually warm, but it's difficult to predict when. But I wanted to show you one interesting prediction of when, which is from this high resolution CSM. So I've talked about the historical trends on top, showing this eastern cooling, a Southern Ocean cooling. But there's a pretty dramatic reversal as you go into the future, looking at the trends from 2023 to 2050. There's a really strong El Nino-like warming in this model. So this shows there's a really strong time evolution of the forced response pattern in this model and has interesting implications for teleconnections and cloud feedbacks going into the future. So one thing I didn't really address yet so far is, does resolution really help with this? Or is this just a coincidence that CSM high resolution happened to be a really good model for this particular ITZ index and aspect of the SST trend pattern? We don't know for sure, but I wanted to point out a few things that are pointing that resolution might help. One is that none of the models that are shown in blue here on the low bias end of the histogram have very low resolution. They're all around the 100-kilometer resolution mark. That's amongst the highest resolution of CMIP6. And in my group, we've run an icon resolution hierarchy, just atmosphere only models, so it's not quite comparable to the bottom plot. But there are still ITZ bias in an atmosphere only model. And we're finding systematic bias reduction from 160-kilometer resolution down to 40-kilometer. 5-kilometer, we've also run, it doesn't quite improve things further, but it doesn't make things worse. And so there's some indication that resolution is helping in a more controlled setting where you don't have the coupling with the ocean. But there's not really a huge change in the atmospheric processes resolved between 160 and 40-kilometer resolution. Based on this, we kind of have the hypothesis that it's probably about the topography. There's important sharp topography, as I've already pointed out, around the Central America, but also the very sharp wall of topography along the Andes. And so we think the improvement in ITZ is likely to do with the topography in South America, and then is something that should be, you don't need 5-kilometer resolution to address. It's happening much earlier. 40, 25, 10 should be a good place to look for less biased ITZZs. So how much time do I have left? Perfect. So I wanted to briefly talk about another thing we might gain from increasing resolution. And here it's really illustrating the role of the atmospheric mesoscale in how this could affect climate variability and climate predictability. So another problem focused more on mid-latitudes that has been around in climate models for some time is that they have too little multidecadal variability of the atmospheric circulation. So this is showing from a paper by Isla Simpson in 2018, the multidecadal variability of the zonal winds at 700 hectopascals in reanalysis on the left and in a large ensemble of climate model simulations on the right. And so there's a dramatic difference in the multidecadal variability of the atmospheric circulation. And this is also true in other models and other fields you could look at, even sea level pressure. And in this paper, Isla showed that this multidecadal zonal wind variability was related to SST changes, so that there's a regression relationship between SSTs and the zonal winds. So suggesting there might be some connection between maybe SSTs forcing the winds or vice versa. And based on this and some other work, which I'll show in a second, we've developed the hypothesis that with increased resolution, you can have the SST anomalies in mid-latitudes increase going higher into the atmosphere because there's frontal processes resolved, and this might help the atmosphere respond more to decadal SST variability. So this is in a large part coming from also some nice work by Arnold Shaya and co-authors looking at how resolving fronts and going to high resolution in really short simulations with NWP models might increase the frontal ascent in response to SST anomalies, for example, over the Gulf Stream. And so basically what we're thinking could happen is that in a conventional climate model, you'd have this warming more trapped near the surface versus when you resolve fronts in a high resolution model, so these are atmospheric fronts, you have more communication of the surface warming aloft, and this can lead to deep warming and something like a jet shift in the large scale circulation. So to test this, we've used the variable resolution capabilities within the CSM2 climate model, where variable resolution has primarily been used in more of a regional modeling context to look at the downscale impacts of large-scale changes. But here we're using it in the opposite sense of looking at the upscale consequences of resolving mesoscale processes on the large-scale circulation. And we've run 30-year specified SST simulations with this setup, looking at a control climatology, seasonal evolving climatology, and 2 different idealized SST anomalies, importantly with the SSTs at 1 degree resolution. So we're really looking at what's the impact of increasing the atmospheric resolution in isolation, because we're then running with this nice 14-kilometer grid shown here, and also a 28-kilometer version of it, and a uniform 110-kilometer resolution to compare it to what's more typical of an atmospheric model used in CMIP. And using this variable resolution means it's about 1/10 the cost of running this 14-kilometer globally. So before showing the results, just want to highlight what this looks like qualitatively in terms of how the differences in an extratropical cyclone look. So this is showing the high resolution versus the 100-kilometer resolution with some low pressure system picked based on where it's crossing over eastern Canada. And you see this nicely resolved cold front going over the Gulf Stream region in the high resolution model, also some gravity waves on the eastern coast of the US and Canada at really fine scales. And then compared to that, the 110-kilometer resolution looks much more like this big blobular structure, not much going on small scales. And to test how this modifies how the atmosphere responds to perturbation, we ran a very simple test where we just increased the SSTs in the Gulf Stream region and looked at how the atmosphere responded in 30-year simulations. And the high-resolution model showed a doubling of the atmospheric response with an NAO-like spatial pattern compared to the low-resolution model. And mechanistically, there's a lot more details in the paper, but mechanistically, this comes about via communication of the warming from the forcing region aloft. This is showing a sector zonal mean over the SST anomaly, and showing a deep warming extending up to 400 hectopascals or so. That's much weaker in the low resolution model, and a much stronger cross-frontal circulation in the atmosphere. And so this is basically then the mechanism that I discussed already, where when you resolve fronts, the air parcels can ascend much more rapidly within these fronts, and this can lead to a deeper warming and something like a jet shift through thermal wind balance. And there's important implications of this for predictability, because if you can predict SST anomalies on seasonal to decadal timescales, and if you have a larger response to those SST anomalies at higher resolution, this means you could have more predictability in the atmosphere and impacts over Europe at a higher resolution. And this is also linked, I think, to the signal to noise paradox, although I don't have time to discuss that today. So will increased resolution improve climate projections? I think very likely yes. I've shown two cases here where it can help. In the latter case, resolving weather fronts increases the vertical coupling that can communicate between SST anomalies in the upper atmosphere and lead to large circulation responses to mid-latitude SST anomalies. It seems that there can also be systematic improvements in the precipitation climatology with resolution, and that this can influence the forced and unforced SST variable trends. And I'll say here that I was focused primarily on atmospheric resolution, but there's of course been a lot of work, including by some of you in the room, how ocean resolution can also improve mean state biases in ocean and atmosphere-ocean coupling. So I think looking at the combination of this increased atmospheric resolution, which was my focus, with increased ocean resolution, I think has a lot of exciting opportunities. So how much should we increase resolution? Do I have a couple minutes, or did I out of time? So I wanted to briefly discuss how much we should increase resolution, because it comes with great cost compared to ensembles and comprehensiveness of our models. I just wanted to highlight a figure here from a perspective paper by Tapio Schneider, Ruby Luing, and myself that was talking about the balance of resolution versus process understanding versus AI in the future of climate modeling. Or this is kind of evaluating where we've come, looking at the improvement where blue is better across precipitation, long wave radiation, short wave radiation. So improvement from CMIP3 to CMIP6 has shown systematic improvement. This has been especially the case in some models, like I'm showing in the bottom left, the improvement of the NCAR climate model. And then high-res MIP shows some systematic improvements with resolution in the middle panels here. Highlighting two that have these three different resolutions. And then if you look all the way to the right into NextGEMS, comparing with a CMIP6 model, these NextGEMS models do have mostly systematic improvement with the exception of precipitation and icon. They've had some problems there. I think they're getting close to addressing those as well, and it's not a systematic thing about high resolution models that have problems with precipitation, but it's an icon specific thing. So, but I'll note that there's a lot of improvement at this high-res MIP type scale, and then a little bit more, or maybe not much of any more at this NextGEM scale. So somewhere in between, there's probably, you're getting diminishing returns. And there's also no clear scale break at these scales. So this is showing the turbulent kinetic energy spectrum. Draw your attention in particular to the bottom, showing the cumulative energy. In the vertical is the orange, the vertical winds. And you're not really getting any clear scale break between 10 kilometer and 100 meter resolution. There's not really a perfect place to put yourself in terms of grid spacing on this spectrum. So I think there's not really a strong argument that we need to push for 1 kilometer. I think 10 kilometers is a good starting point, and it's already where we can explore the implications of turning on off deep convection and do some more experiments. So where do we go from here? And I wanted to talk just outside perspective, how does EERIE fit in? And say that when I give this talk in other places, I often advocate that we should be doing exactly what EERIE is already doing. So basically extended 10 to 20 kilometer simulations where we can learn more about climate variability and change, but still go beyond what's possible in CMIP by including new processes. And still have low enough resolution that we can run long simulations and or ensembles that we need to study climate. And I think what can be really valuable here is quantify the added value of increased resolution by changing the atmosphere and ocean resolution separately and comparing across a range of resolutions to understand where the optimums are in terms of how we can set resolution to really simulate in a good way climate variability and change and improve climate projections, then also hopefully feed this information back into CMIP or run some of these models for CMIP. And just a few analysis ideas coming from what I showed in the talk here is that looking at the amplitudes of decadal variability in the tropical oceans and extratropical atmosphere could be promising things to look into and in control simulations, and that this vertical coupling over ocean eddies, when you do have the advantage of resolving the ocean mesoscale as well, could be really interesting to look into the implications coming up from the work I showed in the second part. So thanks.